Okay, so let's generalize what we saw in example 3 for all rational functions. So if we take a look at this formula, y equal to an xn plus dot 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 over bm x to the m plus dot dot dot, we'll have the following characteristics. So the in behavior asymptotes, if n is less than m, so if the degree of the top polynomial is smaller than the degree of the denominator polynomial, the in behavior asymptote is y equal to 0. And we've already seen that in previous lectures. We've already known that to be true. Now, if n equals m, so if the numerator has the same degree as the degree of the polynomial in the denominator, then our asymptote is just going to be the leading coefficient of the numerator divided by the leading coefficient of the denominator. And if n is greater than m, so if the numerator's degree is larger than the denominator's degree, our function is just going to continue to increase in value as we approach infinity. So it's never going to actually approach any horizontal line. And we can think about it if we look at this y equals qx. So all this is really saying is if our function r of x is f of x over g of x, remember rational functions are of the form, write this out, r of x equal to f of x over g of x, then as x approaches infinity or negative infinity, our function is going to behave just like the function of f of x divided by g of x, if f of x over g of x is equal to q of x. I see, I made a mistake. Q of x. Then if there's a remainder, the remainder won't actually really affect the limit. So as x approaches infinity or negative infinity, our function's behaving like the quotient when we divide f of x by g of x. Okay, so those are in behavior asymptotes. Now, what about vertical asymptotes? So we already know these basically only occur when we have zeros of the denominator. That provided, though, that we don't also have zeros of the numerator at the same value. So what do I mean by zeros in the numerator at the same place where we have zeros in the denominator? Well, let's take a function r of x equal to x squared over x squared. Well, where would we have a 0 in the denominator? We would have a 0 in the denominator where x equals 0. But at that same spot we have a 0 in the numerator. So what does this function actually look like if we were to graph it? Well, it would just be a horizontal line at y equal to 1. So even at the point where it crosses the y-axis where x equals 0, our function is still just defined as 1. So there's no vertical asymptote at x equal to 0. So we're still looking for 0 in the denominator to find vertical asymptotes, but if we have a 0 in the numerator, we have to investigate further to see. So x-intercepts, let's take a look at those. So just like our vertical asymptotes depended on the numerator and the denominator, x-intercepts depend on the numerator and the denominator. So we want to have a 0 in the numerator because 0 over anything, let's say x, is equal to 0. But we can't have 0 over 0 and easily say that we're going to have 0. 0 over 0 is not equal to 0. And y-intercepts. Where are we going to have y-intercepts? Well, that's easy. That's still if we just plug in 0 for x, we know our graph will cross the y-axis at that point, if it's defined.